Well, I think we can go ahead and get started if that sounds good. Sure, Chris.
Yeah, great.
So, thank you everyone for coming out in person and coming online. It is my great pleasure to introduce Chris Stark, who is the Deputy Observatory Project Scientist for JWST here at Goddard. And his research covers observations and theory related to planet disk interactions, disk dynamics, and optimizing future direct imaging mission designed for scientific yields. Chris is also a member of the technical assessment group for the Habitable Worlds Observatory. And finally, he serves as our Lord Commander and Protector of the Realm. So Chris, I turn it over to you. Thank you so much for coming out.
Thank you. I've never received that introduction before. I appreciate that. So today I wanted to talk about a paper that appeared on Archive a couple weeks ago. I don't normally put my papers on before the referee report is complete, but my co-authors here suggest I do that because a lot of the topics I'll be discussing are important to the tag. And so I wanted to start off by rewinding about 5 years to 2019 when the LUVAR final report came out and when I published a paper in 2019. And we were predicting the expectation value of yields for future direct imaging missions like HWO. And back then we put these uncertainty bars on the plots. And we didn't really have that great of understanding of what the astrophysical uncertainties were. They were kind of approximations. We didn't have a super good way of including those in the yield calculations. And we've come a long way since then. And we are now able to do that. The thing you will see from these plots is that the astrophysical uncertainties are large, right? And so unfortunately, we weren't in a position to be able to ask the question, how do we budget for these uncertainties? Because we didn't really know what they were. The answer, of course, is the title of the talk, which is science margin. And you may have heard Mark Clampin use this term in some of his talks. And so I'm going to try to define today what science margin is and how much of it do we need to actually be able to budget for these things. So before I get to that, I will have to provide some obligatory slides that review what exoplanet direct imaging yield is and why we care about it. And in essence, we care about it because it's a really good metric that relates performance parameters of your mission to scientific productivity. Okay, so by learning about what the yield is and how it's sensitive to different parameters, we can better understand how to design the mission. And at its core, what a yield calculation is effectively doing is it's taking known nearby stars in the sky. These are bright enough you can see with your naked eye, and it's playing make-believe. So it's distributing debris disks and planets around them, simulating observations of them with a coronagraph. And it does this and simulates an exo-Earth imaging survey end-to-end many, many thousands of times, and of course, the expectation value of the yield. There are obviously a lot of inputs that go into something like this. We have many inputs that describe the universe as we know it. These are astrophysical inputs. Maybe how common are potentially Earth-like planets, or what is eta Earth? How bright is the exozodiacal dust around these stars? We know that there will be dust that effectively acts like a fog that you have to see through. And we need to know how bright that is. We have observational requirements, like what wavelengths do you want to observe at, do you need to observe at to detect key molecular features like water? And we have technical descriptions of the instrument itself. How big of a telescope do you have? What are the performance parameters of your chronograph? This very large list of inputs get fed into a yield calculator, and it simulates the survey. And today I'll be talking about a yield calculator I've been developing for over a decade. It's called the Altruistic Yield Optimizer. And I'm using the term optimizer there specifically because it's a really important part of yield calculations that I'll get to in a moment. Now, you may be asking, how do we calculate the yield of exo-Earth candidates when we have no idea where they are? And that's a really good question. Effectively, what we are doing is we are calculating them in a statistical sense. So instead of calculating whether we've detected any individual exo-Earth, we calculate the probability of detecting an exo-Earth around a given star if it exists. This is a quantity called completeness. And to calculate completeness, we take a single star and we distribute a very large number of synthetic exo-Earths around it, maybe 10 to the 5th of them. We sample all the radii and phases and orbital elements consistent with our definition of an exo-Earth. We illuminate them with starlight and we calculate their exposure times. Once some fraction of that synthetic cloud, as I've shown here, is behind the inner working angle of the chronograph and difficult to observe. Another fraction is in crescent phase from our vantage point and difficult to detect within a reasonable exposure time tau. The fraction that remains is the probability of detecting that type of planet around that star during this observation, if it exists. The yield of this observation is then simply the completeness times the probability that the planet actually does exist, which in this case is 8/3. And so we do this for, let's say, all 13,000 stars in NOAA's HPIC catalog. We then prioritize them by the observations that are most productive, and we add them up until we've exceeded some survey limit for our mission, let's say 2 years. And we get the total end-to-end mission yield, the expectation value of it. Now, the thing that is a bit different about AYO compared to some other calculations is that it does a lot to optimize its observations. And so effectively what it's doing is it's plotting the completeness as a function of exposure time, and then using the derivative of that curve to make decisions. So it ends up distributing incrementally infinitesimal amounts of time effectively to the most deserving observations. We showed back in 2014 that this does better than some other techniques that are plausible. Why is optimization so important? Well, basically, we always want to make sure we're playing to the strengths of the mission. And sometimes it's really hard to intuit what those are. So what I'm showing you here are scatter plots of the optimized target lists for 3 different chronograph mask designs. These came from the CDS study that I'm co-leading with Russ Belikov. And what I'm plotting is their luminosity versus distance. The kind of faint gray dots you see in the background are stars that could have been selected. The colored dots are those that were selected, and they're color-coded by habitable zone completeness. And as you can see, the target lists are very different for each of these different chronograph masks. So if I had come along and said, well, my mission has to observe a solar twin at 10 parsecs, like we like to say, you know, that would have been a good target here for the DM-assisted apodized vortex chronograph, but it would have been at the absolute limits of what this SPC could do, and it would have been at the absolute limits of what the 16-channel PIC can do. So that would not have been a good fiducial star to judge the relative merits of these different chronographs. So we want to make sure that when we do yield calculations, we're always playing to the strengths of the mission. We're selecting stars that have the easiest observations, and this will help us avoid introducing biases into trade studies. AYO does a lot to optimize these observations. It's not just selecting which stars are best to observe, and it's not just selecting their exposure times, it's selecting the number of visits per star, the delay time between those visits. It's even now selecting what wavelength we observe at on a star-by-star basis. You can send it 8 different chronograph masks. You can assume your mission has a suite of chronographs and assign them on a star-by-star basis optimally. We're even to the point now where we are optimizing the size and shape of the photometric aperture that we're using to extract the planet signal. So at this point, I think we can relax and assume that we are optimizing confidently, and that when we perform trade studies with this tool, those trade studies are relatively accurate. Now, calculating yields is fun and good and all, but at some point you have to choose an absolute yield goal. So how do you do this? How do you choose what our goal is for the mission? Fortunately, we kind of don't have to do this. The Astro 2020 decadal told us thou shalt observe 25 potentially Earth-like planets. But you know, the question becomes, how did the decadal arrive at this number? And I can't speak for them, but I can give you some idea of how I think they arrived on it, because I served on the panel that fed a number like this up to them. And so what I have here is a demo that I thought about doing for probably a decade and never done it, so today's a good excuse. This is a very large bowl of caramel M&Ms, and they're nice and spherical. They look like planets. And I have a cup here that I'm going to dip in here. This cup represents my survey. And I'm going to randomly draw roughly 12 M&Ms. And you can see in this sample of roughly 12, I have 0 blue M&Ms. Now, if I were to pour that back in here and repeat it and do this again, in this case, I have 3 blue M&Ms. And if I did this an infinite number of times, and my bowl was infinitely large, and I replaced it every time, about 68% of the time, I'm going to get at least 1 blue M&M. Okay, and that's because I ensured that 10% of these M&Ms are blue. This is just basic Wilsonian statistics, and you can relate the sample size of M&Ms, this yield of M&Ms, to the fraction that are blue with a given level of confidence, right? So if our sample size is 10, and the fraction that are blue is 10%, I'm going to have a 68% chance of getting at least 1 blue M&M. If I want to increase that confidence to 95%, I have to go up to 25 or 30 M&Ms. And this is where that 25 number likely comes from, because we can relabel these axes the yield of XOR candidates And we can replace this horizontal axis with anything you want to learn about. Let's say F sub life. So what this says is if we want to design a mission that is sensitive to F sub life of 10% with 95% confidence, then we need a sample size of 25 to 30 exoplanet candidates. So this doesn't make the decision for you, but it provides you with a statistical framework that allows you to understand the gamble you're making with the universe. What I think is more powerful is the statistics that underlie finding at least one blue M&M are the same as the statistics that allow you to constrain that number if you don't find the blue M&M. Right, so we can relabel the title here, the exo-Earth candidate yield required to constrain F sub life. So in the event we find 25 or 30 exo-Earth candidates and none of them show signs of life, we can constrain F sub life to be less than 10% with 95% confidence. And that's tremendously powerful. What that is saying is we're not just designing a telescope, we're not just designing an observatory, we're designing a well-quantified experiment that if it's conducted in the right way, guarantees a useful scientific quantity that answers the question, how alone are we? And that's a really powerful idea. And there's precedence for this in history. If you look at the Large Hadron Collider, there's a really fascinating story about how the Large Hadron Collider discovered the Higgs. Does anybody know the name of the collider that was trying to find the Higgs boson that didn't find it? No. It is the Tevatron. It's in Chicago, and there's a really fun story about why they didn't find the Higgs boson. But I think arguably the reason that LHC beat them is because their goal actually wasn't just to detect the Higgs boson. Arguably, their goal was to rule it out of existence. So they were aiming for a very powerful null result. And I was talking with Sarah Eno at the University of Maryland many years ago, and she had this quote that I wrote down at the time, which is, I asked her, how did they end up with a machine so much more powerful than what they needed? Because they found it immediately. And she said, any accelerator is so fabulously expensive that there has to be a guaranteed discovery. Nobody will fund one if there's a chance it will come up dry. So their guaranteed discovery was either detection of Higgs or ruling it out of existence. Our guaranteed discovery is either remotely detecting biosignatures or being able to constrain their frequency and how alone we are. Now, this is all good. I didn't have to bring these M&Ms to illustrate Bosonian statistics to you. In fact, I'll pass them around, and please take a very large survey of them because I don't need to take those home. But I brought these in because it gets more complicated than this, right? We are not guaranteed, if we design a mission with an expectation value of 30 exo-Earth candidates, we are not guaranteed to find 30 exo-Earth candidates. And Dmitry Sobronsky showed this back in 2016. We know that yields are inherently uncertain. And so we need to understand what is controlling the uncertainty in yields so that we can develop a science margin budget for it. So what I'll be doing now is going through the different sources of uncertainty that affect yield. I have a demo here to show you, like, viscerally what is going on, again, using the M&Ms. And I'm going to layer them up one by one until we get to the final total astrophysical uncertainty. So what I'm going to do is I'm going to take this one cup here, which has roughly on the order of 12 M&Ms. There's 12 small cups in this box. They each represent a star. And each of them has a translucent film in it that represents 3 zodiacs of dust. So it's going to be kind of hard to see the M&Ms, right? And I'm just going to distribute those randomly to stars. And if we reveal our stars here, this is our telescope on this end, right? And it's looking this way. And so much like reality, we're going to assume that the distant stars are much harder to observe than the close stars. And so maybe we run out of time right about here. And so to this side of that divider, we're able to survey those stars. To this side, we are not. And as you can see, looking at this group of stars, the yield is a little bit less than the expectation value, or maybe on the order of the expectation value, right? However, if these had been distributed differently, we would have a much smaller yield. So this is just sampling statistics, right? Where the planets are, what stars they are around affects what our yield is going to be. And we wanted to take this into account in the yield calculations. So we started with a 6-meter inscribed diameter version of LUVAR B. Basically, LUVAR B, exact copy of LUVAR B, but we shrunk it down to 6 meters inscribed diameter as recommended by the decadal. And we ignored every astrophysical uncertainty except for exoplanet sampling statistics. And this is the distribution that you end up with. You can see it peaks at about 24 exoworth candidates, on par with the decadal's recommendation, but it's very broad already. So we are going to have to budget for large uncertainties to start with. And what's more is you cannot solve this uncertainty. You cannot retire this uncertainty in the timescale we have to design the mission. So this is inherent to a blind survey. The only way to get rid of it is to know where all the planets are ahead of time. And we're probably not going to know that in the next few to 5 years while we have to design the mission. For the next source of uncertainty that we'll add on here, I don't have a really good, I don't have a fast way of doing this. Imagine I replace all the M&Ms with brown M&Ms or yellow M&Ms, and the brown ones are obviously going to be a little bit harder to see than the yellow ones. So we wanted to look at the idea of introducing uncertainty in the exoplanet albedo. Now, we don't know what the distribution of albedo is going to be for these planets, but that doesn't mean we can't play around with fictitious distributions and see what happens to the yield. So we worked with Ty Robinson and he gave us 3 different plausible distributions of exoplanet albedo. We have water worlds ranging from very dark to very bright water worlds, very dark to very bright rocky worlds, and then we have a constrained range of water worlds in which it's a little more realistic amounts of cloud cover, and we explicitly chose it such that the mean geometric albedo is that of an Earth twin. On the left, what I'm showing you are the yield distributions. The black curve is the same black curve I just showed you, in which every exoplanet has a 20% geometric albedo. The gray, blue, and green curves are what happens when you start introducing a range of albedos. And as you can see, the curves don't really broaden, but they shift to the left. And this is because there's an observational bias that is occurring. The plots on the right, the dotted line shows the injection rate of planets of that albedo, and the solid line shows the recovery rate. So you can see the solid line falls off when you're fainter than an Earth twin, but is otherwise flat above that. Basically, what this is saying is planets fainter than Earth twins are hard to detect. Some of them go missing, and so your yields are systematically shifted to lower values. This is the main impact of this source of astrophysical uncertainty, and we're going to see this again in the next source of astrophysical uncertainty. So what I want to show you next is the idea of exozodi sampling statistics. So we already said that exoplanet sampling means where the exoplanets happen to be, what stars they happen to be around. In reality, exozodi is going to vary from star to star. Right now we have 3 zodies around every star, but in reality there's going to be bright exozodi, there's going to be faint exozodi. So if we assume our distribution has 2 stars with very bright exozodi, and I'll add some more translucent paper to these 2 cups on the end, 2 out of 12 have bright exozodi, and 2 out of 12 have no exozodi. Then you can see we can observe these 2 stars very quickly because they have no exozodi, meaning we can now have time to observe another star that's farther away, and the yield would go up a little bit. However, if these 2 stars happened to be here, we would have to skip them because we can't observe planets around the systems. The disk is just too bright, we can't see the stars. We skip past them, we gain time, we get to move out 1 more star, but that star is a worse star than those 2. So that's going to drive the yields down. We took this into account by adopting the LBTI's host survey's best distribution to their data set. So Bertrand Menacin delivered that distribution to us. We then drew 500 times and assigned exozodi values to individual stars. To every star, we repeated that whole process 500 times. And when you include that, you go from the green curve shown here to the orange curve. And so again, the yield is being systematically driven to lower values. And this is because of the fact that when you assign a bright zodi level to a good target, your only option is to replace it with a worse target. So there's another observational bias that is coming in, driving it to lower yields. For the next source of uncertainty, I'd like to introduce the idea that we don't know what the distribution is of exozodi, right? So here I said 2 out of 12 had no zodi, 2 out of 12 had very bright zodi. Well, what if it's 3 out of 12 that have very bright exozodi, right? There's an inherent uncertainty in what that distribution is. So to include this, we worked with Bertrand Menacin again, who sent us 500 different distributions that are all consistent with the LBTI host survey. And they are distributed normally in log likelihood. When we did that, you go from the orange curve to the red curve. And when we saw this at first, we were kind of taken aback because the 2 distributions are not very different. And what that is saying is something really profound. It's saying that if you believe the results of the host survey, you believe the statistical methods used by the host survey, then the remaining uncertainty in the exozonia distribution is likely not going to impact HWO. And that kind of blew our minds. So we went and checked, right? We went and got Eric Ford to do a completely independent analysis. I won't have time to go into it in detail, but he used a completely different method. He used Bayesian statistics instead of likelihood statistics, and he looked at a different model altogether, minimizing parameters. And what we concluded in the end was, as long as your model to fit the data allowed for a large degree of bimodality, in other words, you have bright stars and you have faint stars, then you would basically reproduce the LBTI host survey. So we're going to proceed with that red curve, assuming that the LBTI host analysis is correct. And we're going to include the last source of uncertainty. So the last source of uncertainty is probably the one that immediately leapt into your minds, which is what is eta Earth, right? And if eta Earth is larger, then we simply have a tastier universe. So to include this, we worked with Steve Bryson. Steve Bryson did the Kepler closeout for the official eta Earth occurrence rate estimates from the Kepler mission. And he fed us 500 different values for eta Earth, all drawn statistically from his pipeline analysis. And I think this is the first time where an eta Earth analysis and the uncertainty in eta Earth are calculated self-consistently with the definition that we adopted for the yield. So he calculated the eta Earth statistics in stellar installation space, not in period space. He adopted our range of radii and stellar installations. And when we include those eta Earth uncertainties, you go from the red curve to the purple curve. So the purple curve is our final uncertainty yield distribution, including all sources of astrophysical uncertainty. And as you can see, eta Earth is the dominant source, right? So conclusion so far is that the uncertainty in eta Earth dominates by far, but surprisingly, the second largest source of uncertainty is the one you probably can't get rid of. It's the exoplanet sampling statistics. Now, we'd like to use these uncertainties to figure out how to budget for them. How do we build a mission that can budget for that distribution and still achieve the science that we want to do? And to do that, you have to choose your yield goal. And I showed you earlier that the Astro 2020 decadal said thou shalt detect and characterize 25 XOR candidates. But it's kind of confusing because they also said thou shalt detect and characterize 25 XOR candidates under the assumption that eta Earth is 0.25. And then later they said 100 cumulative habitable. And those are all different goals. And I want to point out here specifically that 100 cumulative habitable zones would actually not only ignore the uncertainty in eta Earth, it's also going to ignore the uncertainty due to the exoplanet sampling statistics. That's probably not what they had in mind. And I don't think NASA is going to build a mission that ignores your two dominant sources of uncertainty. So I will proceed here for the rest of the talk with two metrics. The first is 25 XOR candidates, including all sources of uncertainty. And the second is 25 XOR candidates, including all sources of uncertainty, except eta Earth, which I think is what the decadal was trying to communicate. So how do we use those distributions to figure out how to budget science margin to achieve our science goal? Well, we can take those two distributions, draw a vertical line at 25 XOR candidates. These are the two distributions that correspond to those two goals I just laid out. And integrate the fraction of the distribution that's greater than our goal. I'm going to call this fraction P25. And if you do that for a baseline 6-meter inscribed diameter version of blue bar B, you can see you get very small values, 6% and 32%. That's not particularly encouraging. So our conversation needs to be, how do we achieve a larger P25 value to make sure we're achieving scientific success here? There are two things you can do. The first is to reduce your astrophysical uncertainties. As I showed previously, eta Earth dominates, so hopefully we can have some work here that reduces uncertainty in eta Earth. Steve Bryson has a precursor science program to do that. We'll see if it's successful. But the second main source, I don't think we're going to reduce. So we really need to start talking about the second option here, which is shifting those yield distributions to the right and budgeting for those uncertainties. To do that, you have to understand kind of what's going on and what's currently limiting the yield for our baseline scenario. So I'm showing you a target list plot here of those optimized targets, including all sorts of astrophysical noise, which is like what's kind of random. And as you can see, the red dash vertical, horizontal line at the top, that is due to the systematic noise floor that we've adopted for the machine. So it's very hard to see planets above that. It's effectively impossible. The curved dash line at the bottom represents 1.5 land over D at 1 micron. So this is a very aggressive working angle for that coronagraph, and it's going to be very hard to observe planets below that. So this is sort of our wedge of accessible targets. And as you can see, there's a lot of stars in the upper right corner that we don't observe. And that's because either we run out of survey time, or because the targets at the edges of that distribution have spectral characterization times so long, let's say 2 months, that they run up against, a realistic limit that we've imposed. Either way, the exposure times are too long. So we need to push to higher yields by shortening exposure times. There are 2 options to shorten exposure times. One is to build a bigger telescope. That's a really attractive option because we already know that yield is most sensitive to aperture size. And the second is to improve the system design. And I'll touch on that for the majority of the talk here. But let's first look at the option of building a bigger telescope. On the left are yield distributions for different aperture diameters. As you can see, the yield distribution shifts to the right. You can calculate P25 for each of these distributions and end up with the plot on the right. And you can see that if we want P25 to be 80% or so, you can get there with an 8, maybe 9 meter telescope, but you're starting to push to diameters that maybe aren't consistent with that tilde 6 meters that the decadal recommended anymore. So it's pretty clear that you cannot, just based on the LUVOIR B baseline, you can't get to very high P25 values while budgeting for eta Earth uncertainties with diameter alone. Now, what is going on when you increase the aperture size? You are reducing your exposure times. This is showing you a distribution of spectral characterization times for the first 18 ExoEarth candidates. I won't get into why I picked 18, but you can see as you push to larger diameters, that distribution shifts to the left. It's even more dramatic than what is shown here because the y-axis is logarithmic. And we're reducing the mean spectral characterization time to find water vapor from 22 days, which, let's face it, is way too long to search for water vapor, to 3 days. So a huge reduction in spectral characterization time by going to a larger telescope. The other thing that is happening is we are pushing to the upper right corner of those plots I showed you earlier, but at the same time, we are reducing that lower curve, right? So the 1.5 land over D curve goes down as you increase D, and so you're gaining accessibility to targets that previously you couldn't access. Yeah.
Wait, no, that what? Which is the black and which is
The black line is 1.5 land over D for a 6 meter inscribed diameter, and the red dash line
Is the variation. Okay.
for the aperture.
Gotcha.
listed area. Okay, so this moves us to the third option, which is to improve the system design. And what do I mean by this? Well, the LUVOIR and the HABEC studies, they were really powerful studies that taught us a lot about how to build a mission to directly image exoplanets, but they were limited in scope, they were limited in time, person power, and so they were not fully optimized for yield. We've also learned a lot since then. We have a lot of new ideas about what to do. And so we have a lot of lever arms to pull on. So what I'm going to consider now are 6 design changes, and none of them are design changes that have a huge impact on yield. They all have a relatively modest incremental impact on yield. But in the end, they're going to compile, much like compound interest, right? So as much as I hate the term synergy, it applies here. These are synergistic changes. Now, some of these design changes are going to, some are not going to pan out. Some will require large technological investments. So they're not all necessarily realistic, but we need to understand what they are so we can figure out the right path forward here. If you're trying to find out ways to reduce exposure time, a good place to start is the exposure time equation. So back when we started out the study, I looked at this equation. The mass equation is up top, and then each term is broken down below. And you start trying to identify terms that you can change to reduce exposure times. And you can look at the end-to-end throughput term, maybe due to the reflectivity of your mirrors. You can look at the bandwidth of your observations. You can look at this factor of 2 in the numerator. I'll get to that in a little bit. Detector noise we'll address, and we'll also look at the core throughput of the coronagraph. So I will go through these 6 changes. We're going to layer them up one on top of the other, and you'll see how the yield evolves as we compile these changes. So the first change is to look at the end-to-end reflectivity of your system. And the LUVOIR mission had 3 chronographs operating in parallel. One of them was a UV chronograph. And because the UV chronograph operated in parallel, that meant all of the pre-chronograph optics had to be aluminum. And aluminum has a lower reflectivity than silver. There were 7 of these aluminum optics, so we had a major reduction in throughput. So the change I'm suggesting here is we don't get rid of the UV chronograph necessarily, but we put it at a different point in the image plane, so it doesn't operate in parallel. When you do that, you lose the fact that the UV chronograph can help contribute to detections, but you more than make up for that with this large increase in end-to-end reflectivity shown on the right. So when we make this change, our yield distribution is going to go from the black baseline curve to the red curve shown here. Our yield is increased by 15%. Spectral characterization times are reduced by a factor of 1.4. And you can see this bar plot on the right. This is going to plot P25 as we compile these changes. So the solid bars correspond to the solid lines, dotted bars correspond to the dotted lines. Let's make another change. So we lost our parallel chronograph channel. Let's now add a parallel vis chronograph channel. And here specifically, I'm assuming that the dichroic that splits these 2 channels is selectable. So we can move either of these channels anywhere in the visible wavelength range that we want. They can both contribute to detections near 500 nanometers. They can both contribute to spectral characterizations near a micron. One of the main advantages of this is if you're doing spectral characterization to search for something like water vapor, there's a lot of water vapor bands ranging from roughly 600 nanometers all the way to a micron and even longer wavelengths. So the broader your bandpass, the more of those absorption features you get to see, and the lower SNR you need to detect it. So you go from an SNR of 5 at 1 micron to an SNR of 4. Sounds small, but SNR gets squared. And we're going to move from the red distribution to the orange distribution. For our third change, we're going to look at that factor of 2 in the numerator that I showed you. That factor of 2 assumes angular differential imaging, a type of PSF subtraction in which we observe our target star, and then to remove the residual chronographic speckles, we observe it a second time at a different roll angle. We then de-roll the second observation, subtract them. We end up with positive and negative copies of the planet, both of which can contribute to SNR, but we've effectively doubled the background count rates of all of our sources, right? Not necessarily a good thing to do, but that's all that, we have to work with. A lot of people have started talking about model-based PSF subtraction. The idea is you either have a method of learning what those speckles are over time, or you collect ancillary data about your system and are able to directly model them. Either way, that would remove that factor of 2 on there. So model-based PSF subtraction would move you from the orange line to the yellow line. That's another increase of 23% yield, reduction in exposure times by a factor of 1.6. You can see P25 shot up now because the expectation value of the curve is beyond our goal. We can now start talking about swapping out detectors. So the LUVOIR-B baseline was a very optimistic description of an EMCCD. They assumed 90% QE at 1 micron, factor of 10 better clock-induced charge than what is currently being demonstrated by the Roman CGI. So here we're going to assume that we move to a skipper CCD. We'll adopt the QE curve shown on the right. We'll adopt the noise parameters shown on the left. And the noise parameters are much, much lower than that, the EMCCD. I should point out that these noise parameters were demonstrated basically in a mine in the center of the earth. And we're not going to have that much shielding. But they show that inherent noise of the detector is not at a level that impacts us. So if we can achieve that by modeling out all these other sources of noise and removing them from the data, then this is the result. You move from the yellow curve to the green curve. We have another increase of 17%, another reduction of 1.5 in the exposure times. If we take replacing the detector to the nth degree and adopt a noiseless energy resolving detector, then we lose our noise terms altogether. Additionally, you get rid of all of the IFS optics. So here the detector itself resolves the energy. You don't need all the lenslet arrays. This increases throughput of the system. And you go from the green line to the blue line. Now, this looks like a small increase in yield, but a noiseless energy resolving detector gets us something else that's sort of not described here. And these are plots from Alex Howe's recent paper in JADIS that shows on the left, not only does a noiseless energy resolving detector increase your yields by about 30% compared to the LUVOIR-B baseline, but you would get spectra for hundreds of additional planets for free. And this is because when you are surveying to find your exo-Earth in broadband, anything that is brighter than that, you're going to get spectra. It's all spectra all the time. There is no separate broadband imaging mode. And so anything that happens to be bright enough to get a spectrum of, you would get. Finally, I haven't touched the chronograph masks at all. So here we're going to swap from the deformable mirror-assisted vortex chronograph, baseline for the LUBAR-B report, to a PIA chronograph. I believe this is a 4th order PIA with a 2.5 Landover defocal plane mask. And you can see that the contrast, which is shown as a dotted line, degrades quite a bit, maybe a factor of 5, the contrast gets worse by. But the core throughput, shown by the solid line, increases by a factor of 5. And this means that any star whose exposure time is not dominated by starlight will have reduced exposure. And it turns out that's a winning trade. So we go from the blue curve to the purple curve. So in the end, we have nearly tripled the yield. We have increased P25 to nearly 90%, even when accounting for Eta Earth uncertainties. Exposure times have been reduced dramatically by more than an order of magnitude. We have pushed far into the upper right corner of that plot, even without moving the lower boundary downward. Here's a table that lists a summary of all those changes. One of the columns in the middle says the reduction in characterization time to detect water. You can see we can reduce it by a factor of 11. And the increase in yield, as I mentioned, is nearly a factor of 3 end to end. But importantly, all of these changes look relatively minor, right? So 10%, 15% increase in yield. Those aren't amazing numbers, but they all compile in the end. There are likely a lot more changes we haven't considered. How am I doing in time?
You got, that's 4 minutes.
Okay. So let me go through a couple of changes we didn't put into our paper, which are kind of fun, that we started thinking about. I mentioned reducing the number of aluminum coatings. Well, what if we actually try to optimize the coatings themselves? And the first place your mind might go is it's the aluminum coatings because they're poor reflectivity, so they have a lot of room for improvement. So I worked with Manuel to get these coating curves. As it turns out, you can only increase your reflectivity for aluminum by about 1% or so. And if we only have 2 aluminum surfaces, that's not a good place to go look. So then you start looking at the protected silver curves. Here's a bunch of different flavors of protected silver. If you look at the y-axis, they only vary by 1% or 2, but there could be 15, 20, 25 protected silver coatings, right, in your chronograph. And so when you compile those end to end, you can end up with very large changes. We could potentially double the throughput at 1 micron by switching coatings. So this is a really interesting trade. You can see you're kind of trading off end-to-end reflectivity for maybe spectral coverage. So it's an interesting trade. But we started looking at this and we calculated the normalized yield as a function of coating, and you could increase your yield by 5 to 10%. And if you had this magical coating that I'm calling R99, which is 99% reflectivity at all wavelengths, then you could go, 10 to 15% improvement in yield. So an interesting potential trade. Something else that we looked at for Russ Belikov was multi-star wavefront control. So the idea here is some stars have binary stars, and those binary stars just flood your image with starlight that you can't suppress. If you have an instrument that allows for multi-star wavefront control so that you can suppress those binary stars, then you'd see a 5 to 10% increase in yield. It's really hard to see the difference here, but you see some points that are very dark on the left, and all of a sudden are very red on the right. So basically you're removing the binary light that prevented observation of those stars. So we have a lot of lever arms here, and I think it's fair to say that a combination of modest increase in telescope diameter and system design changes would allow us, I would say, to budget for all astrophysical uncertainties if we wanted to, right? If we had the budget and that if it's feasible, we could do that. This could result in a tripling of the yield, more than order of magnitude reduction in characterization time. And then the last point I put here is, I think, the most important point of the talk. So if you don't observe anything else, the last point here is that small changes can compile on this mission. But that can only happen to our benefit if we think about it with the right mindset. Right? So I can't tell you how many times I've heard people say, oh, well, it's only a 10% effect. Don't need to worry about it. And if we all make that assumption, we're going to move in the wrong direction very quickly. But if we reverse that logic on its head, and we all find ways that we can do a 5% improvement, those will compile fairly quickly as well. So I've been talking about how we can use science margin to budget for astrophysical uncertainty. I'd like to now close out the talk talking about how science margin can help budget for performance degradation of the mission. And so the idea is, as we mature the design of this mission, I think it's pretty likely we're going to find more problems than we are free solutions. And so we should expect that the expected science performance will degrade as we learn more and more about the mission. And we should consider providing margin to budget for that from the beginning. Now, how do we do that? I don't know. And I think a lot of the engineers would probably say, well, that's what MUFs are for. We put modeling uncertainty factors on everything to make sure that we hit our goals. And what I'm talking about here is something a little bit different. And I hope to illustrate that here with an example. Most of the degradations to the mission will simply extend exposure. Okay, and so a lot of those you can compensate for either with an increase in another parameter, right? If your contrast gets degraded, you can improve your throughput or your bandwidth. Or, maybe say your survey is a bit longer than usual. But there is one prominent exception, and that is the systematic noise floor. So if the systematic noise floor degrades, that is going to permanently remove targets from our target list. You cannot observe exoid candidates around those stars. It's also set by the single hardest thing that we have to do, which is this idea of picometer stability. So it might be worth thinking about, how do we budget for degradation of that parameter and ensure we don't end up backing ourselves into a corner? I don't think I have time to talk about how a chronographer defines what the noise floor is, so I'll just talk about modeling it. Here is another chronograph performance plot. The black dashed and black dotted lines show you the contrast for a chronograph for different stars. And there are different ways you can model what the systematic noise floor is. You could model it like a post-processing factor on the raw contrast, which would look like the red line. Or you can model, or you can say, that ultimately the systematic noise floor is due to the system's instability, which has nothing to do with raw contrast, and therefore it's a uniform noise floor shown like the blue line. I don't pretend to know what the right way is, but we can proceed looking at both. And so what I'm showing you now is the normalized exoid candidate yield for a fiducial mission as a function of uniform noise floor on the left and the post-processing factor on the right. I've chosen two different yield metrics: detection plus search for water vapor, and detection plus search for oxygen, because oxygen pushes on the noise floor a little bit harder. And you can see that the curves are largely similar. And if you wanted to define, what noise floor is acceptable as, let's just say, a 10% loss in the total yield, then you're talking about a noise floor of a few times 10 to the negative 12. So you have to subtract your PSF residuals to a few times 10 to the negative 12. This is consistent with what Bijan Namadi has put in some of his papers. It's consistent with what Stuart Shacklin's been saying, consistent with what I've been saying for a few years now. So I've seen people quote 3 times 10 to the negative 11. That is probably not good enough. We need to be pushing lower than that. And that is scary, right? 3 times 10 to the negative 12 is a scary number. So we need to ask ourselves the question, what if that's not possible? What are we going to do about it? How do we mitigate a degradation in that noise floor? And so what I'm showing you again is the target list distribution for a fiducial mission. The horizontal line up top is that noise floor, but it's not just a single line. It's actually kind of a fuzzy boundary, because planets have a range of radii and Hubble zone separations and all this sort of good stuff. And if that band moves downward, you can see it's going to remove a large fraction of our target list. We can try to compensate for that by improving throughput or bandwidth and trying to push it to the upper right corner of that plot. But that corner is disappearing, right? As that band moves downward, it's removing from the phase space that we're trying to use to fix it. So it's sort of a losing battle. The only way to really compensate for it is to move the lower curve downward, right? It's kind of like that scene in Star Wars where they're in a trash compactor and the walls are closing in, and it was a Luke that did some stupid shit, like put a toothpick in there to try to stop it, right? And then they went out the chute on the other end. So you have to find what your out is here. And that is the only out that is available to us. Because I already drew that curve at 1.5 lambda over d, the only way to do that is to go to larger diameters. So larger telescopes can expand the range of accessory targets, Palladium type stars, helping mitigate this risk. What if we try to quantify what that risk is? I'm showing you here two plots showing the normalized X-ray candidate yield again for those two different types of noise floor. This time for 6.5 meter and an 8 meter inscribed diameter. And you can see the 8 meter inscribed diameter is less sensitive to degradation in the noise floor, like what I've been saying. But it's not a huge factor, right? So you go from maybe 3 times 10 to the negative 12 to 4 times 10 to the negative 12, right? But you have to keep in mind that these are normalized. So if we make these plots an absolute yield, it looks totally different. So on the left, you can see, let's say 30 X-ray candidates was our original yield goal, whatever, it's really 25, whatever it is. And you needed to hit 3 times 10 to the negative 12. If you have an 8 meter aperture and you still need to hit 30 X-ray candidates, you can do that 3 times 10 to the negative 11 or even higher. So a higher yield, absolute yield, also helps you buy margin for system performance degradation. So degradation to the system stability will manifest as degradation to the chronographic noise floor. We can buy margin to compensate for this. The consequence of that degradation is going to be that our target list shifts to later type stars. So maybe we're not observing a lot of G stars anymore, it's predominantly K stars. So we need to talk with START to make sure that they're sort of on board with this idea, but it is, you know, sort of a natural fallback position to think about. And so I'll close here with these conclusions. I've already covered the first one. Larger apertures can help budget for degradations in the systematic noise floor. And most importantly, we need to think about how we can all find small changes to compile to really make this mission more than we even thought was possible initially. Thanks.
Awesome talk, Chris. So yeah, we have time for a question. So anyone online, please feel free to raise your hand, or anyone in the room, of course, feel free to raise your hand if you have a fresh question for Chris. Daniel, did you want to ask your question, or you want me to read it aloud?
Sure.
Go for it.
Can you see me, hear me? Hey, Chris, great talk. I think we briefly talked about this when I visited a few weeks ago. So in the very beginning, you showed this, how many planets you need to constrain the fraction of planets that have life or something like this.
Yep.
So this assumes that each of these individual observations, you get a clear answer, life yes or life no, right? So did you consider including some sort of uncertainty of this individual measurement in that calculation? Or is there a margin, or maybe you cannot really ask the question of life and you have to adapt the question? How do you deal with that?
That's a great question. So right, that initial, I can go back to it here quickly, but the initial plot I showed that was sort of basic fundamental statistics of sample size, that was obviously basic and motivated by this idea that if you want to learn something about a sample, you have to have the right size of sample to learn anything about it. Once you get down into the details of what does this observation mean versus that observation mean, that's another level of fidelity that is not included in this plot. And we do have people working on that. So Noah Tusho's in the room here, and he's looking at, you know, if you would actually simulate what the data looks like from this mission, and then including all the contaminating planets, and then ask, you know, can I see signatures of a habitable zone in that data? It's a much more complex question than just simply reading off Smithsonian statistics. But this should be the sort of the 0th order level that guides sample design this early in the mission.
Great, thanks.
So, that was fantastic, Grace. For the different scenarios that you listed that we could do, how would you run them? It's like, if there's a way, what would you prioritize?
Yeah, so I tried to put them in order of what was easiest. I don't think anything is easy. Let me skip ahead to the table. But, you know, scenario A, where you try to minimize the number of aluminum coatings, that should be the easiest thing to do. We've already done that with the EACs for Habitable. So we think there's disagreement right now about how many aluminum coated surfaces we have, but we think we can get to 2. There appears to be a path to do that. Scenario B, we're also already doing as part of these EAC efforts. So we have 2 parallel, technically we have a near-infrared channel and a vis channel, but it's flexible enough right now we can think of them as parallel vis channels. So scenarios C through F are sort of the ones that are still hanging out there. I think we can do the optimized coatings. That might not be too challenging. It depends on what level of testing needs to be done to prove that coating. But some of those coatings have already been proven. So it's a matter of picking a coating that's been demonstrated. Wavefront sensing, multi-star wavefront sensing control will be demonstrated on Roman CGI. So we might have a good intuition about whether we can do that in a few years. These other things like, I think the skipper CCD, that is a relatively straight, there's a pretty clear path to that. But some of these other things like model-based PSF subtraction, that's a more complicated system level trade. Energy resolving detectors are very challenging because you have to cool them to sub-millikelvin or whatever and introduce all sorts of system problems. So some of these will be easy, some of them will be hard, some of them we've already sort of incorporated into the design.
Awesome. Richard, do you want to go next?
Yeah, hey Chris, great great talk. I have been thinking for a while about an outrigger telescope to have like an interferometric channel. It seems to me like a lot of that the inner working angle is another place that might be pushed on some more. And thanks for this great talk, Chris, and really enjoyed it.
Yeah, so let me make a point here to be clear about something. I'm showing you here the performance plots for two different chronographs. The solid lines show you the throughput of the planet, basically, the off-axis PSF. And so this DMVC6, it has an inner working angle of probably something like 3.5 lambda/d. It's where the throughput falls to half its maximum value. But there is no reason you can't operate inside of the inner working angle. So you can use this deformable mirror, the DM assisted vortex chronograph at 1.5 lambda/d if you want to. There's nothing stopping you from doing that, but you have to be willing to deal with the contrast that's there, right? Which is why, we're pushing up against that limit for late type stars where you don't need that contrast, and earlier type stars, you're not pushing up against that limit. So inner working angle is not a real thing. It's an unfortunate misnomer. It is not a limit. You can work inside of that. And in fact, I thought somebody had asked about this, so I made a thought for it. There was a really great paper that just appeared on the archive. Here it is. JWC has now demonstrated exoplanet detection 1.8 lambda/d. This is using a chronograph that was designed to operate at 6 lambda/d. And it detected a planet at 1.8 lambda/d. Now we already knew where that planet was. But the point is the same, right? Just because the inner working angle is some number, it depends on what the throughput actually is interior to that, what the contrast is interior to. So for the near infrared, there will be a population of stars that we can observe at 1.6 microns, for example. But it's going to be the closer stars, and it's going to be the earlier type stars we can do that for.
Thanks, Chris.
Awesome. Does anyone else have any other questions for Chris?
Yeah, I have a question. So on your target list plots, what is like the sequence of observations to get to those? So is it like redetections and characterization, or?
Yeah, so for these plots,
Yeah.
for this paper, we did not enforce this 6 visit thing that you're referring to probably.
Okay.
So in the LUVAR final report, we had this fiducial observation strategy where we said, well, you're going to want to go search for planets and find out what's there and measure their orbits. And then once you know their orbits, if you know if they're kind of blue or not, you'd go back and search for water vapor, right? So there was this idea that you had to visit a star maybe 6 times so that you could guarantee seeing any planet 3 times and piece together its orbit. We didn't include that in these calculations. This was just like however many visits the code said and the code wanted to do. And then you include a water vapor characterization. There won't be any difference. If we include 6 visits, that turns out the yield hardly changes. It just changes how it conducts the observation. Instead of going really deep in one visit, it picks them off at crescent or at given space. So I don't expect the result to change.
Okay. Awesome. Bertrand has a comment in chat. He says, great talk, Chris. Just one comment versus the exozodi that you know about. For everyone else's info, given that hosts observed around 11 microns, a large uncertainty remains in the exozodi brightness level might be at optical and near IR wavelengths. My hope is that we will be able to conduct a sensitive exozodi survey at HWO wavelengths with CGI to remedy this?
Yeah, that's a great point. So there is a remaining source of astrophysical uncertainty that we did address, and that is how you convert the LBTI host survey into a visible wavelength flux and what the range of fluxes is, things like that. And that's a really complicated problem because it requires, you know, an understanding what the spatial distribution of Exoplanet is and the albedo distribution. And it's sort of a rabbit hole that's easy to go down, but hard to get out of. So that is not actually included in our uncertainty distributions.
Let's do it. Oh, well, perfect timing that,
Yeah.
it decided to,
That's
SharePoint decided to quit on us at that exact moment. Well, I think we're pretty much out of time anyway, so let's thank Chris again for the great talk.
Thanks, Chris.
And- Go ahead.
Just say it back.
Thanks. And if anyone has any other questions for Chris, please feel free to get in touch with them and we will see you next time. But thanks everyone coming out online and coming in the room. I'm gonna go ahead and shut down the meeting.
If you want more M&M, please take them.
Please take them.
Donuts too.
Yes.